John here. We have so far talked about all the parts of the video display processor, the VDP, except for the Sprite state machine and this Sprite module right here. So let's get closure on this. Big thanks to everybody that likes and subscribes to my channel and my Patreons. Really, thank you, especially the VIPs listed here. All right, so what are we going to do here? We have, okay, last time I talked about how I broke this state machine up into these two sub-modules and how everything comes together in here. I'm not going to repeat that. Back up in the playlist. I'll link to that in the description below this video on YouTube. You can go find all that fun stuff in there. So let's focus on the Sprite state machine. So we've got plenty of stuff going on in here. I threw in a little bit of doc in here to talk about what this really does. This thing scans the Sprite attribute table. It looks at all 32 sprites, one after another, in stacking order, in priority order, to find the first 4 that are to be visible on the line that's being rendered on the video output at the moment. When it gets those 4, it's going to put each one of them's pattern into a single register that only has the bits for the current row, because why would we care about the other ones at this point in time? And it simply shifts those pattern bits out one by one and sets the colors accordingly. That's what the whole thing is going to do here. Now, what else do we got? I had a couple of notes here. Sprites are only rendered and collisions are checked only during the active portion of the display area. In other words, if you have 2 sprites partially off the screen and they're behind, the left or right border or the top border or whatever, and they happen to be colliding up there, it doesn't count. They're only checked to be colliding or not colliding if they're in the active display. This state machine will never assert DMA read tick during the active display region, okay? Talked about this last time. It's critical that we don't have the Sprite state machine and the general graphics, the tiles and all that stuff, the patterns and the characters and whatnot, trying to fight to get access to the VRAM at the same time. So it turns out that there's more than enough time in the horizontal during the border, the left border, the right border, and the horizontal synchronization period to fetch and scan the entire SAT. So that's how I'm keeping these things separate. All right, we'll see a little bit of that below when we decide to proceed in the state machine and when we don't, okay? Now, the Sprite state machine has all the same inputs and outputs as the graphic state machine and the parent module. I explained all that last time as well. And this one has, what else does it have? It has an additional parameter. We need to know how much VRAM we have and how many bits there is in the address bus. Went on that in the playlist in the past. All this stuff was discovered before, blah, 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 blah. Till we get down here. These are the only new ports in the Sprite state machine module. And what they specifically mean, I put in some comments over here. Now, what we already know is that there's a status register in the VDP that contains various values. So far, we've only talked about the frame flag over here that goes true at the bottom of each frame that's been rendered so that you can keep synchronization with your CPU code and what the video display is doing at any point in time, so you can render, a flip book movie for video games and stuff like that. Now, we have 5th sprite, and we have a collision, or a coincidence, they use that word, and we have the 5th sprite number over here. So these 3 fields, we'll see how they work in a minute, are these here. So this state machine figures out, the short of it is, are there 5 sprites on a given row? As you know, there can only be as many as 4. And once there's a 5th one, we set the 5th sprite flag to true. And we also want to remember in the state machine it'll save in a register and then output it out this port here, this fifth sprite ID number, which sat entry is represented by that fifth sprite. And we also have the collision thing here, right? So that's this stuff down here. And the collision, of course, means that there's a non-transparent pixel in at least two sprites that are in the same place at the same time. So if you have one that's like a donut with a hole in the middle and another one that's a dot, they aren't colliding if the dot is visible through the donut hole. But they are colliding if a front sprite obscures a back one, okay? So be careful how you understand or in your mind define what a collision really is. And none of this stuff applies if the, well, actually the fifth doesn't matter. If there's more than five, there's more than five, regardless of whether they're behind the border or not. But this, the collision is only concerned when it's in the active display area, okay? Now, these flags get set, and once they're set, they stay on. It's like that frame flag in the status register over here. Once it's set, it stays on forever until the CPU comes along and reads this and kind of consumes the data, all right? So once that happens, that's what this signal is used for. And the way if you trace through the code, this thing comes into this module from the top level module of the whole thing. And it is true when the I/O decoding is such that the CPU is reading from the status port, right? It's the same signal we talked about in the past that is used to reset the interrupt and the frame flag, okay? When that happens, we zero all this stuff out, okay? And color out is going to be the color that comes from the sprite logic only. And we already talked last time about how this color out and the color out that comes from the active display graphic area are combined with a priority encoder where the sprites take priority over the background color in the tiled graphics and all that other fun stuff. And a note here, in case you forget, if you ever poke around in this code, remember that if this is set to 0, it's transparent. And when it is transparent is when you will see the graphic tiled, patterns and stuff. And if those are transparent, you'll see the background color, okay? And if the background color is transparent, as I think I mentioned even in last video, it would be black, because there's nothing back there, and black is what will show through. All righty. You got the usual state machine kind of setup. A whole bunch of reg variables in here to hold the current state and to prepare for the next state every time the system clock ticks. All right. And what do we got here? Any special notes that we have to care about? Yeah, these are the fifth sprite and the collision stuff. This same stuff with the VRAM that we talked about at great length before from the regular graphics part of the screen. And I felt the need to put some doc in here because what we're doing now, note to future self, is might be a better way to do this that could save ourselves some hardware, but it really depends. And I'd love to hear always, never ever hesitate. Hesitate and think out your statements before you make them, of course. But, if you have any kind of constructive criticism, it's always welcome on this channel. Don't worry about my feelings. It's not likely that someone's going to hurt my feelings about some hobby projects that I do. Okay? Which is what these are. But yeah, if you find a better way, when we talk through all this, you'll start to see that what I'm doing is I store a bunch of state information in these registers. As I compile them up, I read a bunch of items out of this sprite attribute table and store them in here one at a time. And when I'm all done, what I do is I assert this sprite load tick signal for one clock period that's targeted. You can see there's 4 of them. So there's one of these for each sprite. These all get either like a cache. We pick them all out of the sprite attribute table. And then we assert a tick signal to send it into one of 4 sprites that are generated here. And that sprite state information is valid for the current line that's going to be rendered. And this also has a latch to hold each one of these values while this is doing its job. And we'll look at this thing in a minute. This is much simpler than the current file, so hopefully we'll zip through this quickly once we understand how it's getting used. Anyway, the point is that I don't know if it's a good idea to have these things sitting here, or more accurately, these three things sitting in here in these latches for a while and then transferred into here, or should I transfer them directly into here, or maybe this thing doesn't have latches at all and I just do them. I don't know. I'd love to hear any opinions on how this can be done more efficiently if it can. All right. It turns out, as we'll see inside here, the horizontal position is actually a counter, and they all have a separate counter anyway, so it might be that the only benefit I could get is to eliminate this and that, which is not a whole lot of bits. Like I said, very internally conflicted, as you can't, if you can't tell on this subject. But if there's anything I'm overlooking, let me know. Okay, this is a weird and wonky thing here. Remember what happens when we have an array of vectors. What we have here are 4 sprite out instances, I guess we can call that, or 4 elements in an array of 4, where each one of the items in the array has 4 bits. And what this is for is the 4 sprites all have their own sprite color out value, which is a 4-bit, color code. So there's 4 times 4 total wires coming out of all 4 of these sprites. And we'll see this in array notation is somewhat handy, because if I use a generate statement, I can just have a counter and just say, the sprite color out sub, 1, 2, 3, 4 is to be connected to each one of these 4-bit vectors. Okay? The same thing happens with the load tick reg. Plus down below in the state machine, I can just set load tick reg to 0 to clear out all of them at once. I don't have to do all, a whole bunch of lines of extra code to manipulate all this fun stuff. Okay? If you haven't seen this before, the short of it is I'm asking the compiler to generate source code. That's what the generate statement says. And I talked about like genvar and what. So what happens is, this is what we call a generate for, and the compiler runs this for loop, and when the for loop body executes, if you think of it as an execution, what we're really doing is we're kind of expanding this as a macro. So what I'm doing is I'm saying I want 4 of these, because I say from 0, while less than 4, add 1. I name this module that is kind of being created in, so this, I name the body of this for loop inst for instantiation. This needs to have a name. This is kind of wonky, because you end up with 4 things in your code that are all inst, but this kind of exists because they're all going to be called S, and I need to have 4 of them, and if I really want to directly address one, how do I do that? So this is kind of an interesting naming thing. You'll sort of see it when we run the simulation. These will all be inst S, and so on. But, if you're looking at the waveform, you're familiar with the source code, and you can make sense of what's going on. And you'll see the 4 of them and how the thing represents itself. Alrighty, so the short of it is, as usual, we need a clock, we need a reset signal, and notice I have an extra one in here, and I say if I'm getting a system-wide reset or a locally defined sprite reset signal, which I use this to reset all the sprites at the beginning of every line before I go to render them. This thing tells all the sprites to turn themselves, in a way they get shut off. All the sprites are running all the time in my particular design, but when I reset it, what happens is it will internally zero out all the pattern bits, and because 0 is transparent when it comes out of the output of this thing, what it really does, if you reset a sprite, it has a horizontal position and all this other stuff, but it doesn't really matter because it becomes invisible. All right? Which is the number one most important thing as far as this logic is concerned, so that it won't be garbage on the screen if it doesn't get configured. after it has been reset. And that will happen if you don't have a sprite on the current line. All of them will just sit there and be invisible and not get configured. Moving on, what happens in here? If you read the manual, you know that what you have is a table, and that looks like this, okay? We got these 4-byte entries in this sprite attribute table. We talked about this last time. The U that probably should have been called V, and so on. So 4 bytes for the first entry, number 0, 4 bytes for 1, 4 bytes for number 2, and so on, up to number 31, which is the 32nd of the 32 sprites. So we need to scan through it all until we reach the end of the table as a whole, or we encounter a sprite whose vertical position is equal to this value here, right on the manual. All right, there's a sentinel position that says if you scan through all the sprites, their attributes, you run into one whose vertical position is that, stop scanning. You're done. All stop, quick, quiet, ignore the rest of the sprite attribute table. That's what that means, okay? And we'll see how that works below. Obviously, we have a loop that's going to read all those entries. When we find this, we break out of the loop. That's what's going to happen here. What is all this fun stuff? And these are our working variables that we use to count this off reg. What is this thing? Nice comment. It's used to scan the SAT. Well, gee willikers. In what way? Right? Okay. So the SAT offset is the number of bytes into this table. The number of bytes, not the index of the entry. Okay? That's what that SAT offset thing is used for. And we'll see that I use that when I'm calculating the address that I send off to the VRAM when I say, hey, I want a value I want to read out of the SAT. Okay? Sprite counter. This thing counts from 0 up to 3, and then you'll see it wrap back to 0. You can tell it's going to do that based on the number of bits. But the idea is we got sprites 0, 1, 2, 3. It's funny that I put a 4 over there. I would give somebody a lot of crap for that. There we go. It counts from 0 to 3 is what it does. Save, please. Okay. And then, like I said, if you then add 1 to it, it goes back to 0. And that fact will be used below in the code. Little foreshadow. That's how I find out that I've got my 4 sprites. And again, when that happens, when I roll this counter over, is when we'll stop reading the SAT table. I've got all of them that I want. We stop. All right. I'm lying a little bit because it does continue on until it gets the 5th one. Then it will end and so on. All right. We'll see it in the state machine. All righty, what do we got here? Row number and name reg. So what happens here is when we're fetching out these values from this table, the vertical position, really I translate that into a row number. And I need to read that in, and I need to do some math on it to figure out if the row number represents a part of the sprite that's on the current line that I want to be rendering, okay? And so I need some variables to deal with that fun stuff. And the name reg simply holds the name reg from the current SAT entry as I go. And I use that as part of the address calculation. And I just scrolled back up here, asking myself in my head, why didn't I bother to put it up with the other ones that I use? It turns out these, in my mind, are related to values that propagate into the sprite controller. All right, the ones down here are used in the state machine as the name and the row number that I'm currently on, or the counter, the number of the sprite, is of 0 interest to the sprites themselves. Okay, so there's 2 different groups here, and I'm like mentally trying to figure out why did these get separated. That's what I was thinking. Okay. What else do we got? We got a state number that we got to get track of for our finite state machine. And clearly this is a one hot state machine. I've named each one of the states. These are all powers of 1, 2, 3, 4, 5, 6, 7, 8 are not powers of 2. However, if you're going to name your states like this, you'll see I shift left like this one right here. What represents the value of the idle state? Well, you take the number of the state, if you're going to count like this, and you say take a 1-bit value and shift it left, however many spaces are being represented by this state number here. And I have enough bits in my state register to hold all the possible bits down here, okay? And this gives me a way to name my states so that I can keep track of what the heck's going on. We look at the code below. This is the usual state machine register. It's a little unusual that this doesn't get initialized to 0, but I got a one-hot state machine that I'm building, so one of them has to be hot. And when is it going to be? It's going to be the idle state. And we'll see the idle state is where the state machine spends 99% of its time, where it's waiting to be told that the rest of the VDP is getting ready to render a new line to initiate a SAT scan. Okay, but all the other stuff gets set to 0 in the usual way. All the things end up the current value equals the next value that comes from the second always block of the 2 always block finite state machine. What do we got going on down here? Now, this is somewhat of an artifact of the fact it used to be that everything was in one big file. It became 2 files. Again, I could use some constructive criticism on this. Is this style a good idea, or should I use a different style? And when I was kind of previewing this thing, walking through this to prepare to record this, I noticed I have 2 different styles in the same file at the same time. So I'll give you a great example of 2 different ways to do this kind of thing. 1, I declare a wire in a continuous assignment that simply says that what I wanted was a variable that represents the current VDP row number. Remember, the rows go from 0 to 191. There's 192 total rows on the screen. And I want to know what row number on right now. And remember, we're rendering onto a VGA screen. It's twice as many rows. So what I need to do is divide this thing by 2. But I want to round it up. And I want to offset it based on the top of the screen, the top border size, which is 48. Yes, this probably should be passed in and derived from the VGA sync generator and all that. I got this is just me being a lazy oaf. I just said, moving on, let's get the code done. I suspect I'll have to go through and clean this up at some point anyway, but I happen to know this works, as far as I can tell, perfectly. So it's good to release your code, even if it's got a little rough edges in style-wise, if it's working. Get a snapshot. So this is that snapshot for me. So what does this thing do? It's going to take the VGA pixel row number, round it up and divide it by 2. The sprite delta, we'll see, gets used below, and this is the thing that represents the distance between the current row number that's being rendered, that I calculated up here, and the origin, the top row number of the current sprite that I'm fetching out of the SAT table. You'll notice I'm grabbing it from VRAM D out. That's because this thing here, it turns out, will only be valid when I'm reading from the video RAM and I have just fetched the vertical position, okay? So the scope, the utility of this thing is somewhat limited. I mean, for me to put this out here, if I was writing like a C program, I would put this right in where the code is going to consume it and then let it go out of scope and discard it at that point. But that's not really how you do it in Verilog. I mean, you got to build a circuit to do literally this. This is what it's going to do, whether I put the code up here or down inside. And it kind of begs the question, should this be in your face like a hardware schematic or hidden, buried in the state machine? Again, this is a style decision. But that's what I'm thinking. And the weird thing about this, it was true about this, by the way, but it turns out that the pixel row is valid over the course of the entire screen, and in your mind, this always will make sense. This down here is only valid in one specific state for each individual sprite when I'm scanning the SAT table, because it's consuming this ephemeral value here. It strikes me as something that I would never tolerate from my students if it was in a C program. Okay, I'm just saying. What do we got here? We got another variable that I, laughing at myself, because when I originally wrote this code, I said equals, and I had a big expression over here. And then I said that expression is getting very big, very ugly, very fast. And this is the other example. So here's one way to do this. I can declare some wires and not assign them values at all, and then assign them values down here in this always block that's a combinational circuit, because that's all this is anyway, right? Or I can, which is what I'm about to show you here, or I can have them in line like this, all right? Because that it's really the same thing. Well, why is this one different? Okay, so in my mind, it turns out that, you know, if I have to consume, 500 characters of space to write this expression, let's put it down here on a multi-line so we can all understand it more easily. Here's what happens. This thing is used to represent how many pixels there are in the vertical and horizontal dimension of this current sprite. If we look at the this Sprite attribute table in one of the two documents you see all the time on my channel, for the 9918, there's this table down here, and it says, look, what's the resolution? The resolution refers to how many VDP pixels, and remember there's 4 VGA pixels in 1 VDP pixel. How many VDP pixels does each pattern bit represent when I'm rendering a sprite? Because there's this magnification concept, all right? So if the magnification is 0, every pattern pixel is 1 VDP pixel. And if I can have a sprite that's 8 by 8 or 16 by 16 based on some configuration bits in VDP config register number 1, I either have an 8 by 8 or 16 by 16 depending on the size. An 8 by 8 has 8 bytes of 8 bits to cover the entire rectangle. If I got a 16 by 16, I need 4 times as many, all right? Because it's too wide and too high in terms of the 8 by 8 tiles that fill this whole thing, and that's how they did it. I talked about that last time as well. Now, if magnification is set to 1, what happens is we just magnify every pixel that's in the sprite that we would have otherwise rendered up here. An 8 by 8 turns into a 16 by 16 in visual size, and a 16 by 16 turns into a 32 by 32, again, in visual size. And the way we do this is just like when I convert the VGA pixels and double the number of columns and rows to represent 1 VDP pixel, I just double it again. So this is 2 VDP pixels wide and 2 VDP pixels high for every bit that is in the pattern. Okay, and if that's not immediately obvious, scan around these manuals. They got some diagrams in here, and you can think it out, and it should make sense after a few seconds of thinking if it's not obviously right off the bat. All right, so what happens here? How do I do this? Well, in order to determine which size I got to implement the truth table you just saw over there. It's got 2 input bits, and I determine what my size is going to be. Is it going to be 8 by 8, wide, the width and height, and 16 and 32, and so on, right? So I need to know how big that is to figure out if they're overlapping. When I use the value of this sprite delta, which as you can clearly see here, it's the distance from the top line of the current sprite, which is what's in the vertical position sat entry field. I want to know how far away that is. Well, if it's above me and the number of rows in this sprite is less than or equal to however big it is vertically, I need to be able to calculate that. So I need to know what this is. All right. I also need to know the size when I'm going to render it on the screen. How many bits wide is it going to be? But you'll see that is handled a little bit differently than this. So how is this then done? I got a one-hot case statement, and I got an expression in here. If the size is 1 and the magnification is both 1, well, in that scenario, it's 32 by 32, right? Okay, I'm just implementing that truth table. If the vertical size XORed with magnification is true, that means if this is on or that one is on, but not both of them, then I know it's a 16 by 16. That handles these two cases right here. That's a definition of an XOR, these two lines right here. Then I need to know if it's an 8 by 8, so I simply say otherwise it must be 8 by 8. So this is how I calculate the size. Right? And there's plenty of other ways I could have done that, I suppose, I chose to do this. Okay, the rest of this you've seen before. Set up the next value. Is it going to be retain the current value in most cases? Sometimes I decide that the next value will always be 0, for example, unless otherwise overridden down below. This one is X for the sole purpose of the reality. I mean, think about this, right? If the read tick goes true, and we talked about this at great length, and we talked about the other state machine half, and we talked about the other stuff in the state machine that has to do with the graphics part of the active display, right? If that's true, then the address matters. Otherwise, it doesn't matter. And by putting an X in here, it makes the simulation stand out because it uses different color in the waveform display. And it also could save lots in circuitry and routing if you let the compiler know that you do not care what value comes out of this thing in certain times. Okay, so it doesn't, in other words, it doesn't have to create a 0 when you don't want to use it, because it would have to create circuitry to do that, right? This says, I don't care what you put on there. Okay, moving on. These other ones are all set to 0 up here because I want to have this notion of simplifying the software below. Same with this read tick. Unless I set it to 1, it's not going to generate a read tick in the next state time period. Same with all these other things. Do I want to tell the sprites, one of the sprites, to become loaded with the current values in the registers I talked about above in the next, state tick period? No, yes. By default, don't do anything unless somebody sets it to 1 below. That's what is going on with these. And this one is basically helping me debug this during simulation. This is an illegal state, okay? And that makes it easy to catch because there's a default statement in the case statement to deal with this. And I can print something out during the simulation and halt it and make sure that I can debug my code. So that's why this is in here. Basically, it's instant death if I don't treat the state bits with the proper respect that they're due. It also kind of simplifies the code below because I don't have to zero anything out. I can only set the one bit that I care about that represents the next state. I don't have to clear out the current one all the time. What are we going here? I would argue that would save paper if you were to print this out in the old days. Okay, what do we got here? When the status register is red, we reset all the status bits. Like I said before, they all get set, they get seized on, they get latched on, and they're held indefinitely until somebody reads that status register. So this is the zeroing out of the flag and the fifth sprite and so on. And you can see above here, they are retained throughout all time. The only way they can become set to 0 is in the reset above in the state machine reset, or in here if the status reset bit that's on the port is pulsed true when the CPU reads that status register. Okay, now we get to some other interesting stuff here. This is the collision detector. As I said, if you have 2 sprite pixels in the same place on the screen that are opaque, you have a collision. Now, no one helps you by remembering what sprites were colliding or anything like that. You simply get this flag that says 2 sprites are colliding. Good luck figuring out which ones, but at least you know, okay? So that's the feature based on the chip design. So what did I do in here? Well, we ask, is the color that's currently coming out of sprite number 0 or 1 or 2 or 3, any of the 4 current sprites, I make a 4-bit binary number out of that with the concatenation operator, right, these curlies. And then I match this down like this, and I say, look, if none of the bits are on in this expression up here, because remember, this is a 4-bit value, and I'm comparing it to a 0 or not, so this thing represents a 1-bit truth-false type Boolean value. So this whole thing is a 4-bit number. If all 4 of those bits are 0, that means all 4 of the sprites are currently transparent right now. Therefore, they can't be colliding. If I have only one of the 4 sprites right now is not transparent, then I have no collisions. Otherwise, in all the other cases, there would be 16 total cases, of which I'm looking at 5 here. So there's 11 other cases that have more than 1 bit set to true in here in this 4-bit number. In all those other cases, I do have a collision. This is how I decide whether or not there's a collision. All right? Now, this up here, the whole thing's in this if statement. This exists to implement the I only care if there's a collision when I'm in the active video region. That's what that's there for. And this over here, this was a bug in the original implementation. I'm like, what's going on? I have to ask if there's not already a collision being reported. Then and only then, and it's in the active display, do I do this. Otherwise, no, don't do anything, leave it alone. If you don't limit this thing, what happens is you can get a collision being reported, and then later on the screen, you'll be in areas where there aren't collisions. There's plenty of pixels on any screen, no matter how many sprites you got on there and how big they are. There's always at least 1 pixel on any given screen, frame, I should say, of a screen, where you're not going to be colliding. So what happens is it goes 1010101 all the time when it's drawing the screen. So this exists solely to keep it on once you've set it. And it stays on until somebody reads it and sees it in the status register and it gets reset up there, okay? This is what that's all about. And you'll see another thing down below that deals with the 5th sprite that has the same kind of logic. Once you've reported the 5th sprite, leave it alone. Otherwise, you could end up turning it back off as well, all right? That's what that's all about. Then we get to the main state machine down here for the sprites, the part of the sprites that scans the SAT, okay? So what do we got? We got a parallel case, a one-hot situation here. And let's go to the bottom of the file really quick. This has a default down here, which means it's not really a one-hot. It's a parallel one, because if you have a default down here, it has to deal with the fact that we may have none hot, okay? And the code that comes out of the compiler will change because this is here. This should never happen. It can never happen when the code is complete and debugged properly, okay? It can't happen as, I should say, designed, as intended to be implemented. It should never happen. And I bring this up because I'm looking at this when I was getting ready to record this, and I was asking, why did I put this down here like this when this line probably should be above this default and the end should be down here below this end? And the reason I think that might be useful, the reason I know it might be useful, is because if this is not here, the compiler can do a much more efficient job at using and generating less circuitry to implement this this case statement. If this isn't here, okay? My gut tells me that this should be the whole default should go away when I'm not in simulation. All right, again, I'd like to hear your thoughts. I've, somebody might say, oh, what happens if one of the bits goes off? Well, if that happens, well, what happens if all the LUTs fill up with garbage data? It's not supposed to happen. It can't happen as long as your power is stable and you don't have noise and stuff like that. If you're concerned about circuitry that does not do what it has been programmed to do, and I'm not talking about your intent versus actual and having bugs in there, okay? Once you've decided to release this design, this can't happen, okay? Once it has been debugged, therefore it should go away. All right. If your hardware can't be trusted, then you shouldn't be using an FPGA. Now, that's a different problem. What if a 1 equals 0? Then nothing will work anywhere. This is the least of your concerns, right? So my first state is idle. I already told you what that means. We sit here forever waiting for someone to assert this sprite tick out signal. And I talked about the in and out signals before. They're kind of like named a little bit wonky. Let's look it up here real quick. We saw this last week. The reason I want to talk about this is because I never really showed anybody this before, I don't think. The sprite tick out is right here, and it actually comes from the output of the pipelines that I talked about last time, okay? Now, it originates, the sprite tick that goes in comes from the VGA timing generator, and this is why we're on this little tangent, because I added it to VGA sync long since I first went over all this stuff. And you'll see it coming out in here. There's a sprite tick right here. And it's documented that the next pixel clock time period is an optimal place to start sprite fetching, or to start the scan of the SAT table. And where that is, well, it'll be more obvious when we look at the timing diagram, is it comes out of here. And we all talked about this at great length long ago. And I just simply added it in here, just like, hey, should I be asserting the horizontal sync right now? Should I be asserting vertical sync? What should I be doing? Well, this one says it's true when what? The active display area, okay? And I -1 because we'll see that the sprites are actually fetched at the end of the line prior to the line where they are rendered. So there's this off by 1 jazz. You'll see that crop up again. And what else do we say? And I'm in a horizontal situation where the next pixel will be the right border. So in other words, when, let's say this is your screen here and there's a border, right? The video display has this border around it. When I go from the active area into the right side border, as I'm entering that right side border, that's when this thing goes true for a single tick period. And that tells the state machine over here, it propagates through the various modules, that it is time to begin your sprite scan. Okay, so that's what's happening here. I stay forever in idle until this happens. All right, that's the only way I get out of idle. If I'm in idle and that's not happening, I just stay in idle. And you saw above that I said all this by default. They're all getting zeroed out before I enter in this case construct here. So I have to set it back to idle if I want to stay here. Okay. If it is set, what do? I'm going to move on to sprite vert, which is when I'm processing the vertical position. Because what am I going to do? You're going to see I'm going to read these 4 bytes out of the current entry. That's my goal. I don't need to read all 4 if the vertical position suggests that it is not in range. And we already talked a little bit about that. What's the distance, right? If the sprite starts way above where I'm at right now and can't possibly appear on the current line, or it starts below the current line, then I don't need to read the rest of this junk at all. I just move on to the next one, okay? So that's what's going to go on in our first thing here. So in order to do that, I need to read the first byte of the sprite attribute table for the first sprite, or for the first entry in the table, I should say, right? So what do? I zero out my sprite counter. Remember, that is the 4 visible sprites. It's going to go 0, 1, 2, 3. And then back to 0 if I run into the 5th one, okay? What do we got? The SAT off. The SAT off, remember, is the offset in bytes from the beginning of the sprite attribute table. So the first thing I want to do is I want to read number 0. Now look very closely when I'm using these values. Sometimes I will use something reg, and sometimes I will use something next in here. And this style kind of leaves me feeling like it's subtle, so I'm going to wave my arms around, yell and scream about it a little bit here, because you can really get in trouble with this. It's bad enough we're dealing with a pipeline. This is a 3-stage thing going on, as you'll see here, because what I do in this state won't be valid and useful for two states from now is when the this value will come out of the VRAM, and that can get kind of confusing. And it can also be subtle if I'm using the next value, and I do that because I set it to 0 right here. I need to know what byte I'm going to get, so I'm going to calculate the address based on the offset into the table, which is going to be the first one. Combine it with the base register, and that is what I want to use for the address that goes to the VRAM. Okay, and then I say I want to tick, read tick next to tell the VRAM to start reading, and that'll happen during the next state. It doesn't start now, it starts in the next one. Okay, and then what do we do here? We also assert the sprite reset thing, which you saw above. What this will do is it'll set all the sprites to, basically transparent and blank and all that fun stuff I talked about a few minutes ago. So that's where that all happens. When this is done, the next state is vert. Okay, so when the clock ticks, the state machine advances, I end up down here. There's really not much to do here, but say thank you very much and move on to delta. Why is there nothing to do here? Because this is the time where we're actually doing the reading of the VRAM, and the data from the VRAM will not be valid until the next clock. And we talked about VRAMs and all that delay long ago in this series on the Nouveau. Okay? So we just simply move on to the next one to waste this current tick. Now we're down here in the third state in the sequence, and we say, hey, is what I got out of there, remember I'm reading the vertical position from the sat entry. Is it the sentinel? If it is, I'm done. All stop, quick, quiet, go back to idle, wait for the next. This would be a good time to restart the scan tick to come along, right? If that's not true, I'm going to use the delta on the size that we just talked about at great length. So if the distance to the sprite is less than the size, now remember what the delta is. The vertical position of the sprite, minus the row that we're on right now? I said that backwards. It's the current row minus the sprite position. And the +1 because the top row on the screen, the top VDP row number of the sprite position is -1 rather than 0. And I can throw an opinion on why that might be. I think I mentioned it last time. It's probably because the real chip, either they made a mistake or they decided it was less circuitry. They just declared that the first one shall be -1 because when you're doing all this stuff down here, you're doing it, when you start doing it, I should say, you're doing it on the previous line. If you really think about this, that sprite tick thing goes off in the right border. And the right border of what? It's at the end of some line, and what we're doing is we're fetching the data for the line that will come next. So it turns out that the current row number, when we're doing all this logic, is all off by 1. So it's a misfeature, perhaps, or an oversight, or a simplification of the hardware. It could go either way. It depends on a number of things. Anyway, so the point is the first one is -1, and that's compensated for above, by the way, the +1 in there. So what happens? If the distance is less than the size, we know it's above us, and it overlaps the current line. That's all we care about, okay? And I put all this in here. It took me a few times to think about this. I'm not going to pretend that this is obvious, but I'm not going to spend 20 minutes talking about it. You may want to pause the video, work all this out, ask yourself, gee, is this a signed compare, an unsigned compare, and all this other fun stuff? Okay. Yes, this does work. And if you want to run it and see what's going on when the thing runs the test case, you can see what's all happening in here, okay? In any event, this does it does the right thing. Okay, so sprite counter reg, if it's gone to 4, how can that even be? Did I misspeak earlier? How many bits are in sprite counter reg? 0 to 0, 1, 2. Yes, it can go to 4. I lied. I lied about lying. It does go from 0 to 4. Sorry about that. The doc was correct. Oh, come on. And my editor is bothering me. Anyway, okay. Bottom line, I didn't realize there were that many bits in there. Never think when your mouth is open. That's a huge problem. Huge problem. I suffer greatly from that. Anyway, it can become 4, okay? And if it ever does, then we know we're on the 5th sprite, because the 5th sprite is number 4. And we, like I said, this is the other one that says make sure you're only setting it until the user resets it by reading the status register. If it's not currently set, we say this is a 5th sprite number. We get it by the offset register, but we only pick some of the bits out of there. If you think about that, it's because the offset is in bytes from the beginning of this table. We want to divide it by 4 because it goes 0, 4, 8, and so on when for the addresses that represent the first byte of each of these entries. And that's what's in this offset reg thing here, okay? By throwing away the least significant 2 bits, we're dividing it by 4. And that is the ID number of that 5th sprite, the one that we're currently having just read in, okay? And we set the flag in there as well, all right? So this only gets done on the first time it sees that there's 5 sprites on the current row. Now, there's also room in here for a little misunderstanding because the doc is not clear. Should this be the first time I run into the 5th sprite on the current frame or the last one? And by the way, the whole idea of the current frame is all garbage too, by the way. What this really is, should this be the oldest time, I should say, since the last time I read and therefore reset the status register? Should it be the first 5th sprite encountered since that last status reset? Or should it be the last, most recent 5th sprite encountered since that last reset? Okay? I don't know. I might have to write some special test code and run it on a real one to see what it actually does. I could see it going either way. I don't see it doing anything in the middle. Like, it'll only be the last frame and no, I'm pretty sure it's going to be since the last time anybody reset the status by reading it. Normally, when you care, you'd be reading it at least once a frame. Anyway, and there's some interesting techniques people use to read it more than once a frame. And I talked all about the caveats of having done that due to metastability problems in the design of the VDP itself. So, this is open to a little bit of interpretation when it comes to which 5th sprite we want to talk about. And if you're not following there, think about this. What if I got 5 sprites on the screen here and 5 more sprites down here? Well, is it going to be unhappy about the 5th one up here or the 5th one down here if I read the status register at the bottom of the screen during the time that we're down here? Which one? That's what we got to decide here. So I choose the first one encountered as opposed to the last one. Okay, what do we got here? When that's all done, because we just found a 5th sprite, okay, and we may have updated our status on that, we go back into the idle state and stop scanning the set. What's the point of reading more? There's nothing that could possibly benefit from doing so. So we go back to the idle state. What happens down here? This is the else that has to do with the, running into the 5th sprite. Else, it's not the 5th sprite. Say that 10 times fast. I need to know which pattern row to fetch based on the current row that I'm on the screen right now. Let's take a back up bird's eye view. Let's ignore this for a second. This has to do with the magnification. Let's assume it's not being magnified, and the ternary operator simply says then use this if this is a 0. Okay, so we're not magnifying. What is it going to do? Sprite delta from above gives us the row number of the current sprite. It's being rendered based on the current VDP row that we're trying to paint on the next, scan line across the screen. That's what we're fetching here. And I'm going to try and figure out what row in the pattern table I want to go get based on that distance. Well, if I'm on the very first line of a sprite, then the delta would be 0. And I'm going to use this thing in the math calculation later on when I'm going to fetch the pattern. Do I want the first byte in the pattern, the second byte, and so on? And this is true all the way up to even if it's in 16 by 16 mode, because I explained last time, if you're in a 16 size sprite, all 16 bytes, at least for the left half of the sprite, come one after another in the VRAM. And all 16 pattern bytes for the right half of the sprite are also one after another in the VRAM. So it turns out that the row number, which is, the offset into the pattern for the current sprite, when it's not being magnified, is simply this delta value. If it is being magnified, it turns out I need to divide this in half. I got to discard the least significant bit is what's happening here. Because remember I'm doing 2 VDP rows at a time. So when I'm calculating the offset into the pattern table, I need to use this math to basically render the same sprite row twice and then move on to the next sprite, I should say pattern row in the pattern table twice and so on. That's what's going on here. Set offset next. I got to advance this by 1 because remember that's the byte offset into the sprite attribute table. So I'm currently pointing at the vertical offset. I want to go ahead and I want to read this. I want the horizontal, the name table, and the color. I got to read these other 3 things. So as the state machine progresses, you'll see this thing advance one at a time. To prepare for all the subsequent bytes that we need to read. We'll see another situation here where I'm going to give the VDP address based on this calculation using the next value, not the current one, same as before. And I'm going to assert this to say during the next state, go get it. And the next state is going to be I'm waiting for the horizontal position to be fetched. That's what this is doing. Else, this one says what? I'm not in range. That goes with this one up here. I'm not in range. So what do? I need to move on to the next sprite and see if that one's any good. So, yeah, I'm not in range. What do? Well, instead of advancing 1 byte, I'm going to advance by 4 because remember, I'm pointing here. I don't want to read these 3. I want to skip down there. That moves me down 4. Then I say, what? Is the offset next equal to 0? Aha! There's another problem we got to wrap around. This counter here has just the right number of bits in it to represent all the size of all the entries. It's a power of 2. If I go 1 past the end of my 32 entry table, I end up with 0. And if that happens as a result of this addition here, because I'm asking about the next, not the reg here, again, the new value, if it becomes 0, I know I ran off the end of the table. I'm done. So I go into idle, just like reaching the sentinel. Okay? Otherwise, there is something there. Go ahead, calculate the address based on the offset, just like we did above, to restart the reading of the next entry in the attribute table. Set the tick. And go back to vertical fetch, which is above here. It's that extra period that we have to go through, the extra time for the memory to send us our results and then ask the same question. So this is it polling, 1 at a time, bang, bang, bang. It's going to go all through 32 entries if none of them are visible or on the current line, and it'll eventually end in here if that is the case by running off the end of the table and becoming idle there. Okay, if it did decide to read in, found something, and it wants to move on, it moves down to this state here. There's nothing to consume from the video memory because remember that the previous state only prepared and sent the address of the horizontal value from the attribute table when I enter this state. So this is when it's actually being read, and it's not until the next state down here that I actually can get it. from the memory. All right. Again, this is a 3-stage pipeline. Got a lot to think about in here. So what are we going to do? After this one, we're going to move on to the horizontal state. There's nothing really fancy. We know we need to consume this data, so the rest of this state machine is more straightforward than what happened so far. What are we going to do? We're simply going to then what? Advance the counter and get ready to read the value after the horizontal. So we don't even have the horizontal yet, and what we're doing is moving our registers around to say during the next state, we got to get the name table entry, and when it's doing that, we're preparing to get the color entry and so on. So we're going to see all this, multiple things happening at the same time. So that's what we're doing here. We're saying, I know you're reading the horizontal, but in the next state, I want you to be reading the name table address. So we're going to do this. Again, some debugging in here. Then when we're in the next state after that is this one here, and I started adding some comments that says, I've now got the horizontal value that I wanted. Prepare to read the color, because that's what I need to start for 2 states from now. And when this one's done, move on to reading the name from the VRAM that I just set up here. Okay, and the same kind of thing we just saw above. We're going to move to the next entry in the table and say, give it to me. And I'm now consuming the horizontal position from our multi-stage pipeline. And the next state, I think, moves on to Sprite name, which is down here. And it says, okay, now the name is finally coming out. What am I going to do? I'm going to get ready to start reading the pattern table data using these funky things, and these 2 lines are the things that are really hard to figure out how to do based on the broken diagrams that I whined about in the last video. So that's what's going to go on here, and then after this is done, he's going to advance to a state to consume the color that was prepared for up here, which is what he's trying to get from the VRAM up here when he calculates the color address. So keep these 3 levels all the time in your mind. So what does he do? He takes the name in this current state, advances to the next sat entry. This is done here because above this, remember, already prepared to read the color. That's in progress in this current state. So by adding 1, what we're doing is we're pointing the sat offset to the next one here, getting ready for the next table entry. That's what this one is doing. The next sat sprite entry, not the next sprite with the sprite counter, which is the 4 sprites that we're filling in the data for, okay? All right, what do we got in here? A little note about me griping about the manuals. So what do? We ask about the configured sprite size, not the sprite size variable that we calculated above. Instead, we need to know how to determine the address in the pattern table that we need to use to grab the 1 row, the 1 byte, one of the bytes, I should say, of the pattern table that's needed for the current row and the current sprite. Okay, so what are we going to do? Sprite pattern base followed by the name, a 0 in here, and the sprite row register that we just talked about above. What row am I on in the current sprite? We put a 0 in here. This is because when this is a 1, we're in a 16 by 16 mode. What this is doing is it's calculating the address of the left 8 bits of the pattern for the current row of the current sprite we're fetching out of the SAT. Okay? This roughly matches, I should say, one of these table diagrams here, which is this one. This one's not too bad, okay? Except there's an extra X right there. Okay, this one's okay because this has the right number of bits in it. These is the right bit range. This X there is commented, although in a very non-intuitive way. And then there's 4 bits over here. Okay, when you're in a 16 by 16 mode. If you're in size 0, this is exactly what you want to do. So these two lines, modulo this one extra x down there, represents this if expression in here. So if we're not big, it's easy. It's an 8-bit sprite. Take the base, you take the name, and you combine the bits exactly as shown in this table right here. Here's the base, the 8 bits from the name, followed by what row number you want to get, because you've got 8 rows. You need 3 bits to represent 0 through 8. That's what we're doing here, okay? That's what happens right here. However, if you're in a large one, it's a 16 by 16, you get to venture into the who failed English as a primary language when they wrote this. Okay, so, oops, here we go. What's going on here? This is very close, but not quite right. You know, you don't win the Bozo's grand prize game. Alrighty, sprite base, same as before. You take the name. Notice you can take bits 7 to 2. When we're numbering bits like everyone on Earth other than TI and IBM, otherwise you would take 0 through 5. Okay, so this is the leftmost, I should say, 6 bits of the name value. We ignore the rest. And this has certain implications. This means that if you have a 16 by 16 sprite, when you give it a name, when you configure this sprite attribute entry here, the least significant 2 bits are completely ignored. Their names must be a multiple of 4. And that's not like in your face in this doc either, by the way. But it's definitely implied based on the math that's going on here. Why? Because you're just not going to use those bits. This X here, it says 0 for the least significant byte, 1 for the most significant byte of the pattern. Wow. This, in my opinion, should have said 0 for the left side half of the pattern and 1 for the right-hand half of the pattern. In no way do I see LSB and MSB representing the left and right. Again, I don't know. Somebody probably just throwing around acronyms that they didn't understand when they typed that in or misinterpreted something. I do not know. Because even if you number the bits backwards, these are the most significant 6 bits. In no way does this make sense. That I don't know, anybody. You know, I suppose you could put the bits in the sprite register that we'll talk about in a little while backwards and shift it in the other direction, but that, I don't know, whatever. I don't know. Moving on. Down here is what? Size equals 1 sprite byte number. I do not know what the heck. Sprite byte number? Well, again, jeez. It's the row number again that we calculated above. Wow. They should make the people that actually write the code go back and fix the doc. I don't know. A multi-million-dollar thing. This is not some esoteric thing they sold 4 of and went, you know, and then dumped the product. They were like kings of the hill when this thing came out. Everybody was using them. Somebody must have noticed this. Ugh. I digress. Anyway, you can clearly see how this pattern works. When I want the left half of the pattern, I got the row number, which is a 4-bit number now, because it's 16 rows, with a 0 here. And as I told you before, you got 16 rows in the pattern table, followed by another 16 rows. And they're all starting on a multiple of 4 for the index number. Therefore, the first 16 will always have a 0 is its address in this position. The second 16 will always have a 1 in here for the right-hand half, okay? Again, pause this, walk through it, you'll figure it out, and you can laugh and curse at the manual all you want. This does work correctly. It is right, okay? As far as I know. So we calculate the address with no help from the doc and say, make that one start going in the next state, and we move on to the next state, which is to consume the color, which is already a work in progress, and the next state after that will consume the pattern that we just sent the address out above, and then we want to get the other half of the pattern if the sprite is big. Otherwise, we don't care. There is no other half of the pattern, if the sprite is, when I say big or small, I'm talking about the 16 by 16 versus the 8 by 8 for the small. So what do we do here? I'm going to do this regardless of the size of the sprite and calculate the address anyway using the exact same math, but put a 1 here instead of the 0 because this essentially adds 16 to the address that used last time. And if you think about it, if there's 16 bytes worth of pattern up here, regardless of the line I'm on, that line plus 16 is in the next 16, that'll be the line number for the right half of the sprite. Again, pause it and draw it up if need be to follow that. We're going to run out of time otherwise here. So, and we then set, rather than say read tick equals 1 like I do in all other cases, I set it equal to VDP sprite size. And this is kind of an optimization. Now, I decided we're going to do this whether we need to or not. We can consume the color data, which we know is coming out of the VRAM right now, as well as the early clock stuff, and we'll talk about that in a second. But what should we do after this? Well, if it's a 16 by 16 sprite, we need to go and get the other half of the pattern data. And this will be 1 if it's 16 by 16, otherwise this is 0. And if it's 0, we then say read tick next equals 0. It won't change its value at all. We'll have an address for the VRAM address bus, but we're not going to use it. That's okay. All right? It'll cause a wasted state down below, but you know, as you look at the timing diagram, we have plenty of time to do this. It simplifies the code at the end of the configuring of the sprite if we just fall through all the states regardless of the size anyway, okay? I could put optimization down below. I could eliminate this entirely if I'm not in 16 by 16 mode and stuff like that, right? I mean, we could make some changes. I'd like to hear your opinions on that if you have one, okay? All right, so what happens down here? We got what's coming out of the VRAM, like I said, is the foreground color right now, and we also have what? We know that it's also got the early clock data in the current value, right? So we're reading, what we get from the VRAM is this right here. We get the foreground color, 0 bits, and an early clock, and I talked about that before. That early clock, if it's set, we're simply going to subtract 2 from the value that is represented by this horizontal position up here. Okay, and I talked about why you need to do that in the last video. So this is the logic that does that. If this bit's on, just take 32 off of that. Otherwise, take it as it is. Now, in theory, there would be an offset here. And as we saw before, I actually have an offset set to 0 there. So hpos represents the distance off to the right that it would normally consider 0, which you can use to compensate for borders and things. And I'm pretty sure that if we go back up to the higher level guy here, now we can see in here that it's set to 32. And this is a hard code. Again, I was lazy. I made the Sprite module right, but this one up here, this is, you know, as you just saw, is the parent module that owns the two state machines that deal with the graphics. I just hard-coded the size of the border within here. It should come from the VGA sync thing that does the borders and all that, but I was lazy, so sorry. And again, another thing to clean up. So that's where that value comes from. And why did we look that up? We looked it up because the units for this thing, and you know, what is the column number and all that. Well, it turns out this horizontal position starts at 0 when it's on the far left edge underneath and hiding behind the border. So where this is concerned in my code, it's not the horizontal position that I get out of the SAT. It's the horizontal position after I account for the early clock. So what I decided to do, and this is one of these subtleties, is the units or the range of this thing. This starts at the far left of the border. That's what I consider 0 for the use of the hpos value in the sprite. And I do that so that I can just unify all this other junk. If it starts you know, with early clock or not early clock, the sprite object does not care. The only reason there even is an early clock bit over here is because it couldn't fit up here. And therefore, it's annoying for the user and everyone else on Earth. So what I decided to do is just to say, look, this horizontal position starts at 0 and it goes up behind the border. So the active display region, and even the right border, although it doesn't get used over there, it all is one contiguous range of numbers. And that simplifies the counting logic in the sprite object itself. This minusing of 32 in here is a little bit awkward, probably a waste of some hardware. If we wanted to look at hardware optimization, we could look more at updating or accommodating somehow for the early clock in the sprite register and how it operates its counter in there rather than subtracting 32 here. All right, so this is really a software-ish perspective of how to deal with this rather than a hardware one, because like I said, this might actually generate more hardware than we really need. There may be an easier way to do it in terms of a simpler way for the compiler to deal with this. Okay, so then what do? We fall through to the next state here because, and this is done, it moves on to pattern 1, and now we're starting to consume the pattern data. Finally, and at long last. This is the first byte out of the pattern. Well, what is that first byte? This is always the left half of the sprite pattern, which is what this is going to get used for. If it's an 8x8, it's all of it. If it's a 16x16, it's the left half. No matter what, I store the 8 pattern bits in the left half of this pattern register. And the reason I do that is because when I render my sprite, the position of the sprite is the upper left corner. So if it's only 8 bits, the 8 bits that you see would be positioned in the same place where the left 8 bits would be in a 16-bit wide sprite. And as you recall, during the beginning of the sprite scan, the entire set of all the patterns and all the sprites are all zeroed out as part of the sprite reset, beginning of the line. Therefore, pattern is entirely transparent. This places the current 8 bits in the left half of that pattern register. Okay, so if there are no more, that's exactly what we want. We want to see the 8 followed by transparent. Done. If there is more, we'll get it down here in pattern 2. And this is this extra state that you could optimize away, but you'd have to like replicate a lot of this in the state above and say we still need to deal with all this and start the next vertical scan and all that junk. There'd be a lot of replicated code. So I go through here and I waste the state, whether I need to or not. Okay, if I'm an 8x8, this is a waste of an extra time tick. That's all. But it simplifies the code. And we have time to waste during this period, so I let it go. Okay, so when I'm done with the left half, I go in here, no matter what, okay, which means I either got the right pattern right now or nothing at all. I don't get the right pattern if I never set the tick up here. That's what this is about. Remember, I've got 3 stages in here. I'm consuming that now. All right, so here's the other case we have to worry about. You know, if we may have added one and we moved forward while scanning through the SAT, right? So if we had already wrapped around, but we were finishing the last of 32 sprites, this is where we stop. Okay, if the very last sprite is actually visible, this will happen. If we run out before we get to the 32nd sprite, another state will have already moved us back in the idle. Okay? So this is a special case where the last one was consumed and we wrapped around down here. So what do we got? If we didn't wrap around, what do? We go back to, hey, it's time to fetch the next vertical position, which is the first byte of the next SAT entry, which our offset's currently pointing at for the next one, okay? We recalculate this the same way we did last time. We say, I want to read the next one. And like I said, we go on back to the state where it starts to consume that vertical position data. And here's where we consume what we asked for 2 states ago. Remember, we're in pattern 2 now. We're getting what could be the right-hand half of a 16-bit wide sprite, or we're getting nothing at all because we didn't ask the VRAM for anything. So again, we ask the same question. Is this a wide body? If so, we consume the data that we asked for 2 states ago. Otherwise, we can just set it to 0 and leave it as transparent. Okay? Turns out it already was 0. So running 0 in here is redundant, but it's what you want ultimately in the right-hand half of that pattern. And now we finally get to the point where we're going to say, hey, Mr. Sprite, sprite number, remember 0, 1, 2, 3 here. We want to save the horizontal position and the color and the pattern in the current sprite that we are configuring. Okay? So that's what we're going to do here. Then after that, notice we're using the reg here, okay, and not the next, unlike some of the addresses above. So we say when we're done with this, move on to the next of the 4 sprites we're going to be configured. And of course, the following state is either going to be idle at that point when we're done, or we're going to be consuming more sprite data to set up, possibly set up more sprites, okay? We already talked about this down here, which is, you know, like I said, mainly to catch and halt if I am screwed up and forgot to set the next state. I mean, that's a lot of stuff we walked through. We're probably out of time. So I'm going to end this now. What we'll do is we'll look at the sprite object and kind of tie it all together in a part 2 of the sprite discussion video series here, all right? So, what do you think? Any comments? Like I see, I got some doubts on my style in here a little bit. If somebody's got any ideas on how to maybe, I don't know. I wrote this, believe it or not, for clarity, more so than optimum hardware, you know, minimization and time. You know, I'm wasting some clock ticks and things like that. So I'd love to hear your thoughts on this whole thing. Let me know. Till next time, I'll see you on the internet.